The circle is arguably the most fundamental shape in our universe. It appears everywhere, from planetary orbits to everyday objects like wheels. Today, we'll explore the fascinating relationship between a circle's measurements and the mathematical constant known as pi. Every circle has key measurements that define it. One of these is the diameter, a straight line passing through the center from one side to the opposite side. The diameter represents the widest distance across the circle. Another important measurement is the circumference, the distance all the way around the edge of the circle. If you were to place a string around the entire circle and then measure that string's length, you'd be measuring the circumference. Now here's where things get interesting. Thousands of years ago, mathematicians discovered something remarkable. If you divide the circumference of any circle by its diameter, you always get the same number. This special number is pi, approximately equal to 3.14, though its decimal digits continue infinitely without repeating. This might seem like a simple coincidence, but it's actually a fundamental property of all circles. Let's verify this by looking at circles of different sizes to see if this relationship holds true. Here we have two circles of different sizes. Let's first measure their diameters. Our small circle has a radius of 1 unit, so its diameter is 2 units. Remember, the diameter is always twice the radius. Our large circle has a radius of 2.5 units, which means its diameter is 5 units. Notice how the diameter is simply twice the radius. This relationship is true for every circle. Now let's find the circumference of each circle. For the small circle, we can calculate the circumference using the formula c equals pi times d, where d is the diameter. With a diameter of 2, the circumference is approximately 6.28 units. For our large circle with a diameter of 5 units, the circumference is approximately 15.71 units. Again, we're using the same formula, c equals pi times d. To better visualize this relationship, let's organize these measurements in a table and calculate the ratio of circumference to diameter for each circle. This will show us whether pi truly remains constant regardless of the circle size. Look at our results. For the small circle, when we divide the circumference 6.28 by the diameter 2, we get 3.14. For the large circle, dividing 15.71 by 5 also gives us 3.14. This is pi. The ratio is exactly the same for both circles, despite their different sizes. This remarkable consistency demonstrates why pi is a mathematical constant. No matter how large or small the circle, the ratio of its circumference to its diameter will always equal pi. This property makes pi essential in geometry, engineering, physics, and countless other fields where circles appear. Pi's value of approximately 3.14159 continues infinitely without repeating or terminating. Mathematicians have calculated trillions of digits of pi, yet there's no pattern to its decimal expansion. Despite this apparent randomness, pi emerges naturally from the perfect symmetry of the circle, one of nature's most elegant shapes. For thousands of years, mathematicians have been fascinated by the relationship between a circle's circumference and its diameter. This ratio, which we now call pi, appears everywhere in nature and mathematics. One of the earliest methods to approximate pi used regular polygons inscribed inside a circle. Let's start with a hexagon inside our unit circle, where the radius equals 1. For a unit circle, each side of this hexagon equals exactly 1 unit. With 6 equal sides, the perimeter equals 6. Since the circumference of a circle equals 2 pi times radius, we can deduce that pi approximately equals the perimeter divided by 2, giving us 3.0 as our first rough estimate. Now, let's increase the number of sides to get a better approximation. With more sides, our polygon will more closely match the circle's shape. This octagon with 8 sides fits more snugly inside our circle. The corners don't cut as far into the circle's boundary. By calculating its perimeter and dividing by 2, we get approximately 3.06 for pi. Let's continue our pattern by increasing to 12 sides. Each time we add more sides, the polygon's perimeter gets closer to the circle's true circumference. With 12 sides, our dodecagon follows the circle's curve more precisely. The perimeter calculation now gives us an approximation of 3.11 for pi. We're getting closer to the familiar 3.140. By doubling the sides again to 24, we can see a pattern emerging. Each time we double the sides, our approximation gets noticeably closer to the true value of pi, and the polygon becomes increasingly circular in appearance. At 48 sides, the difference between our polygon and the circle becomes almost imperceptible to the naked eye. Looking at our table, we can see how each increase in sides brings us closer to the true value of pi. This inscribed polygon method was used by Archimedes in the 3rd century BCE. By carefully calculating the perimeters of inscribed and circumscribed polygons with up to 96 sides, he determined that pi lies between 3 and 1/7 and 3 and 1071, or approximately between 3.1408 and 3.1429. The key insight of this method is that as we increase the number of sides, the polygon's perimeter converges to the circle's circumference. Theoretically, a polygon with an infinite number of sides would have exactly the same perimeter as the circle. What's remarkable about this approach is that it gives us a systematic way to approximate pi with increasing accuracy using only the geometric tools available to ancient mathematicians. Our final approximation with 48 sides gives us 3.14, which is the familiar value most of us memorize for pi. This is remarkably close to the true value, which begins 3.4159265. This geometric approach demonstrates how mathematical constants like pi can be discovered through simple yet powerful visual reasoning, connecting the discrete world of polygons to the perfect continuity of a circle. Here we have a circle with a straight line passing through its center. This yellow line represents the diameter, labeled d, which is the widest distance across any circle. Let's imagine cutting this circle at a point and unwrapping it into a straight line. This will help us visualize the relationship between the circle's circumference, the distance around it, and its diameter. We've now transformed our circle into a straight line. This line represents the circumference, the entire distance around the original circle. This transformation preserves the length, so this straight line is exactly as long as the original circle's perimeter. To understand how the circumference relates to the diameter, let's place 3 copies of our diameter below our unwrapped circumference line. Each yellow segment represents exactly 1 diameter length. These blue arrows help us compare the lengths. As you can see, 3 diameters placed end-to-end cover most of the circumference, but not the entire length. There's a small portion remaining, which suggests that the circumference is slightly more than 3 times the diameter. This remaining portion, highlighted in red, is approximately 0.14 times the diameter length. This means that the full circumference is about 3.14 times the diameter, a very special number that appears throughout mathematics and nature. We can express this relationship with a formula. C approximately equals 3.14 times d, where c is the circumference and d is the diameter. This ratio is remarkably consistent. No matter how large or small a circle is, the circumference will always be about 3.14 times its diameter. This special ratio has a name. We call it pi, represented by the Greek letter pi. Pi is approximately 3.14, though its decimal representation never ends or repeats. This irrational number is one of the most important constants in mathematics, appearing in countless formulas beyond just circle measurements. Our unwrapping demonstration gives us geometric intuition for why pi exists. It's not just an arbitrary number, it's the natural relationship between a circle's diameter and its circumference. This connection has been known for thousands of years, with ancient civilizations approximating pi with increasing accuracy. The relationship we've explored shows that for any circle, the circumference equals pi times the diameter, which is approximately 3.14 times the diameter. This fundamental property connects circular motion, rotation, and countless natural phenomena to this special number, pi. The circle is one of the most fundamental shapes in our universe, appearing everywhere from planetary orbits to wheels. Let's explore its key measurements to understand pi. The diameter, shown here in yellow, is the distance across the circle through its center point. This gives us the maximum width of the circle. The radius, shown in green, is the distance from the center to any point on the circle. By definition, every point on a circle is exactly the same distance from its center. Notice that the radius is exactly half of the diameter. The circumference, labeled as c, represents the total distance around the edge of the circle. If you were to take a string and wrap it exactly once around this circle, its length would be the circumference. Ancient mathematicians discovered something remarkable. For any circle, no matter its size, the ratio of the circumference to diameter is always the same value. We express this relationship as c equals pi times d, where pi is that special constant. Since the diameter equals 2 times the radius, we can rewrite our circumference formula as c equals 2 pi r. This form is often more useful in calculations and is the version you'll see most frequently in mathematics. We can rearrange our original formula to isolate pi, giving us pi equals c divided by d. This shows us precisely what pi represents, the ratio of any circle's circumference to its diameter. This ratio is the same for every circle in the universe. This definition of pi as the circumference divided by diameter is fundamental to geometry. If you measure any circle's circumference and divide by its diameter, you'll always get the same value, pi. Throughout history, mathematicians have worked to calculate the exact value of pi. Early approximations simply used the value 3. With better measuring techniques, we've found that pi starts with 3.14159 and continues with more and more digits. Each additional digit gives us a more precise value. What makes pi truly special is that these digits continue forever without repeating in any pattern. This property makes pi an irrational number. It cannot be expressed as a simple fraction or terminated decimal. Mathematicians have calculated pi to trillions of digits, and still no pattern has emerged. Pi appears in countless mathematical formulas beyond just circle measurements. It shows up in probability, statistics, physics, and even in the mathematics of music and art. This single constant connects seemingly unrelated areas of mathematics and science. The relationship between a circle's circumference and its diameter gives us one of mathematics' most important constants. Pi's unique properties and universal presence make it not just useful, but truly fascinating. Pi is a fundamental constant that appears throughout nature and technology. With a value of approximately 3.14, this mysterious number connects countless phenomena across our universe. Let's examine water ripples, a common natural occurrence. When a droplet falls into water, it creates perfectly circular waves that expand outward from the point of impact. As each ripple expands, it maintains its circular shape. Each circle has a specific radius, which we can measure along with its circumference, the distance around the outside edge. Here's the fascinating discovery. For any ripple, regardless of its size, the circumference is always exactly pi times the diameter. If we measure a tiny ripple or a massive one, this ratio remains constant. This is our first glimpse of how pi serves as a fundamental connection between circular measurements. Now let's explore wheels and gears, crucial elements in engineering and transportation. From bicycles to cars to massive industrial machinery, circular motion drives our technological world. When a wheel rolls without slipping, it demonstrates a perfect application of pi. The red dot on the wheel's edge will trace out an interesting path as the wheel completes one full rotation. Notice the distance traveled by the wheel in one complete revolution. This distance exactly equals pi times the diameter of the wheel. This isn't coincidence. It's a direct result of the wheel's circular geometry. Engineers rely on this relationship when designing everything from gears to vehicle transmissions to ensure precise mechanical movements. Our third example explores the pendulum, a device that has been crucial for timekeeping throughout history. Pendulums were used in grandfather clocks for centuries because of their remarkably consistent oscillation period. When a pendulum swings, it follows an arc path determined by its pivot point. What's remarkable is that for small oscillations, the time it takes to complete one full swing is independent of the amplitude, meaning it doesn't matter how far you pull it back, it will take the same amount of time to complete a cycle. This formula shows the period of a pendulum equals 2 times pi multiplied by the square root of length divided by gravitational acceleration. Notice how pi appears here, even though the pendulum's motion isn't obviously circular at first glance. This connection reveals how pi describes not just static circles, but also dynamic oscillating systems throughout physics. Now let's visualize how these three seemingly different phenomena are connected through the mathematical constant pi. Water ripples, rolling wheels, and swinging pendulums all share this fundamental relationship despite appearing quite different on the surface. Let's bring everything together to see the bigger picture. Each phenomenon involves circular motion or measurement in some way. Pi serves as the central connection between these diverse real-world examples. In water ripples, pi relates circumference to diameter. In rolling wheels, pi determines how far the wheel travels in one rotation. And in pendulums, pi appears in the formula that determines the oscillation period. This remarkable constant, approximately 3.14, binds together countless natural and engineered systems through mathematics. The appearance of pi across such diverse phenomena demonstrates how this single mathematical constant unifies our understanding of circular patterns throughout the natural and engineered world. Let's explore the fascinating geometric meaning of pi, one of the most important constants in mathematics. This simple ratio appears in countless formulas and natural phenomena. Every circle has a center point. From this center, we can define the circle's key measurements. In this example, our circle has a radius of 1.5 units, which is the distance from the center to any point on the circle. The diameter, labeled as d, is a straight line passing through the center that connects 2 points on the circle. It's always the longest distance across the circle, no matter which direction you measure. The radius, labeled as r, is the distance from the center to any point on the circle. Notice that the diameter is exactly twice the radius. This relationship is true for every circle, regardless of its size. The circumference, labeled as c, is the total distance around the circle. If you were to wrap a measuring tape around the entire circle, the length would be the circumference. Ancient mathematicians noticed something remarkable about this measurement. When you divide the circumference of any circle by its diameter, you always get the same number, pi. This ratio, written as c divided by d, approximately equals 3.14159, with digits that continue infinitely without repeating. This constant relationship works for circles of any size, from planets to atoms. The first 3 digits of pi, not a 3.14, are why we celebrate Pi Day on March 14th. Though we commonly approximate pi as 3.14, it's actually an irrational number, meaning its decimal representation never ends or repeats in a pattern. Pi's influence extends far beyond just measuring circles. Let's explore how this single constant connects different geometric formulas and appears throughout the natural world and human innovation. The circumference formula states that c equals pi times d. We can also write this as c equals 2 pi times r, since the diameter equals twice the radius. This means that the circumference is a little more than 3 times the diameter, a fact that ancient civilizations approximated even before they fully understood pi. Pi also appears in the formula for a circle's area, a equals pi times r squared. This elegant formula shows that the area depends on the square of the radius multiplied by pi. It's fascinating that both the perimeter and area of a circle involve the same constant, demonstrating pi's fundamental role in circular geometry. In physics, pi appears in countless formulas. Take the simple pendulum, its period depends on pi. The formula t equals 2 pi times the square root of length divided by gravitational acceleration shows how pi helps determine how quickly a pendulum swings. Pi also appears in wave equations, orbital mechanics, and Einstein's field equations. Engineers rely on pi when designing circular components like gears, wheels, and pulleys. The proper spacing of gear teeth, the rotational speed of motors, and the design of curved structures all depend on accurate calculations involving pi. Even electrical engineering uses pi in formulas for wavelengths, frequencies, and signal processing. Nature is filled with pi. This logarithmic spiral, similar to those found in seashells, galaxy formations, and hurricane patterns, incorporates pi in its mathematical description. Pi also appears in the distribution of prime numbers, the structure of DNA, and even in the meandering patterns of rivers. These natural occurrences aren't coincidences. They reflect fundamental mathematical principles. What's remarkable is that all these diverse applications, geometric formulas, physical laws, engineering principles, and natural patterns are connected by this single mathematical constant, pi, approximately equal to 3.14159. This shows how mathematics isn't just abstract theory, but a language that describes our universe. These connections highlight how pi serves as a bridge between different branches of knowledge. When we measure a circle's circumference, we're tapping into the same mathematical constant that governs planetary orbits, sound waves, architectural domes, and even the spiral patterns in sunflower seeds. Pi represents a deep harmony in both mathematics and nature. Pi transcends being just a number. It's a fundamental constant of our universe. From the practical task of measuring a circle to understanding wave patterns in quantum physics, pi reveals the mathematical order underlying seemingly diverse phenomena. This simple ratio between circumference and diameter connects geometry to the physical world in profound ways.